organizers for organizing this and allowing me to speak. And okay, so this is joint work with Octavio Arismendi and Daniel Perales. And today's talk will be about finite free probability. If you haven't heard about this, I want to tell you what it is because I think it's very interesting and exciting. And I also want to tell you about new results that we have in this direction. And just to give a bit of context, finite free probability arose from the work of Marcus Spielmann and Srivastava. In this period of time, 2013 to 2016, they wrote a series of influential papers. And in one of them, they realized that if you look at certain polynomial convolutions with a free probability perspective, then you can learn interesting stuff about polynomials. And well, for me, this closes some triangle of interacting fields, namely analytic theory of polynomials, free probability, and random matrices. And finite free probability sits somewhere in between all these areas. So, okay, the main objects that we will be working with is real-rooted polynomials. So polynomials with real roots. And given some real-rooted polynomial of this form, we'll denote the empirical root distribution by mu p. So this is the measure that puts equal weights in all of the roots of the polynomial, and it's a probability measure. So we normalize so that the total mass equals 1. Okay, so let's begin this talk with a motivating problem, and please feel free to interrupt at any point if you have questions. So this is a question by Steinerberger, and it's purely in terms of polynomials. So it a priori has nothing to do with free probability. So this is the setup. You take some sequence of real-rooted polynomials, PD is of degree D, okay? And you assume that the root distributions of these polynomials converge weakly to some limiting probability distribution that is compactly supported. So for example, if you take the sequence of Hermite polynomials, we know that those converge to a semicircle, right? So that's an example of some natural sequence that satisfies these properties. And then Steinerberger's question was like, okay, well, if this is very large, I know that the root distribution looks a lot like nu. But what happens if I start taking a bunch of derivatives of the polynomial? How does that root distribution evolve? And to formalize this question, what we're going to do is, or what he did is taking some t between 0 and 1, and then taking t times d derivatives of the polynomial, right? So you take a fraction of the degree of the polynomial in derivatives, and you ask, how does this distribution look as a function of t? And here are some pictures I stole from his first paper. So the outer curve represents the initial distribution, and then the other curves represent how the distribution evolves as t goes from 0 to 1. And as you can see, it eventually starts looking like a semicircle regardless of the initial distribution. And that's something that will become clear in a moment why this is happening. And long story short, the description of this evolution of distributions can be stated or is like very naturally stated in terms of free probability. And to be more precise, in terms of fractional free convolution powers. So what are these? Well, we already saw what the free convolution is. So now for any integer k, let the kth power of a measure be taking k convolutions of that measure with itself. Well, Nick and Speicher showed that in fact, for any s greater or equal to 1, even if it's some real number, so non-integer, you can make sense of this convolution, and this interpolates this definition there. So when s is an integer, then you recover that definition, and this forms a semigroup. Well, so it turns out, and this was informally proven by Steinerberger, who made some assumptions about this evolution in order to set some partial differential equations. And later this was formalized by Hoskins and Kabluchko. So they showed that for any t between 0 and 1, the asymptotic root distribution of this polynomial that you get after taking TD derivatives can be described in terms of this fractional free convolution. Okay? So as you can see, when t is equal to 0, then you just have nu to the 1. So that's nu itself. That's because we haven't taken any derivatives. And you assume that the root distribution converges to 1. And as t goes to 1, then this exponent starts going to infinity. And then by the free central limit theorem, we know that that converges to a semicircle. So that's why, regardless of what distribution you start with, eventually you start seeing a semicircle. Okay. Yes. Smaller as that. Well, so the roots interlace as we take derivatives. So
yes. Okay. Yes. Thank you for that. But in this formula, making the measures get higher.
Well, so it says after proper rescaling. Yeah, sorry, I was sweeping that under the rug, but one has to rescale and also account for the fact that you're losing mass, right? So if you take derivatives, then you have less roots. So you also have to, well, if you phrase it in terms of empirical root distributions, I guess you're already implicitly normalizing. Yes, you multiply by a constant. That's a function of t.
Yeah. Okay, thank you.
Okay, yeah, thanks for the question. Okay, so that's the description. And well, we found this, or at least I found this very interesting because there's no operators involved, right? So this is just polynomials, and derivatives are something in polynomial world, and free probability is popping up. Yeah.
Raise their convergence in terms of the free convolution? Like they talk about free convolution.
So Berkeley found some PD that describes this evolution. And then when Dima and Tao wrote their paper, he realized that those PDEs matched his. So he was like, okay, this must be the convolution. And then Hoskins and Kabluchko used the R transform to formally show this. And it's a somehow complicated proof. So, okay. So I want to give you now a very quick proof using finite free probability that we think kind of explains why this connection is happening. And but before doing that, let me just tell you a bit about finite free probability. So finite free probability is some theory that studies polynomial convolutions. So these are operations that take two polynomials and give you back another polynomial. So we'll focus on the additive finite free convolution and the multiplicative finite free convolution, which are denoted in this way. So how do we define the additive one? Well, take two real-rooted polynomials, P and Q, okay? Then, because they're real-rooted, you can find Hermitian matrices A and B, such that P is the characteristic polynomial of A and Q is the characteristic polynomial of B. It doesn't matter which ones you choose, so you can choose whichever you want. And then you can define the convolution of P and Q as the expected characteristic polynomial of the random matrix A plus U star BU, where U is drawn from the Haar measure on the unitary group, okay? So this is just a definition. And it turns out that this convolution has been studied for 100 years. So it was introduced by, although it wasn't known that you could express it as an expected characteristic polynomial. So in fact, you can do something more elementary and just give names to the coefficients of P and Q. So I'll denote them by AIP and AIQ. And then you can say explicitly what are the coefficients of the convolution between P and Q. So those are given by these coefficients here. And that's how they were, well, people worked with these formulas before. And similarly, the multiplicative finite free convolution, you can define, so given P and Q real-rooted polynomials with Q having only non-negative roots, you can define the multiplicative convolution between P and Q by again taking matrices A and B, and then taking this expected characteristic polynomial. So this time the random matrix that you're averaging over is A U star BU. And again, U is some Haar unitary matrix. Okay, so again, this convolution has been studied for around 100 years. And the formula for the coefficients of P convolution Q is this time even simpler. So you can compute the coefficients in this way, and you can even think of this as some alternative way of defining it. Okay, so what is known about these convolutions? Well, many things, but among the most important ones For example, it preserves real-rootedness, the additive one. So if P and Q are real-rooted polynomials, then their additive convolution is also a real-rooted polynomial. That's not trivial at all. If you furthermore assume that Q has only non-negative roots, then again, the multiplicative convolution is real-rooted. And something that Marcus showed, and then Arismendi is that if P and Q, well, you take sequences of polynomials PD and QD that are real-rooted, so that the root distributions of PD have some limit nu P, and the root distributions of mu Q, the mu QDs have some limit nu Q. Then the root distributions of their convolution. So now we're looking at PD convolved with QD using the additive convolution, converge in distribution to the free additive convolution of the limiting measures. Okay, so in this sense, these convolutions are converging to the free convolution. Okay.
That statement, do the degrees have to go to infinity?
Yes. Well, no, sorry, no. Well, no, yes. They do have to.
Finite would be the same.
You can approximate. So the new piece can be some discrete measures on a finite number of points, but you do have to let the degree go to infinity. So throughout this talk, throughout this talk, I'll assume that PD has degree D and QD has degree D. Yeah.
Is there any assumption in that theorem that there's some like uniform interval that contains all of the roots or anything, or it's just weak convergence? Really the forced by the convergence to practice supporting measure. No, because a few of them could, a small fraction of them could be.
Yeah, so they do require that the support of the union of the measures is finite. So there's some interval that contains all of the roots of the polynomials. And later we realized that there's a trick using interlacing that allows you to chop out so you can let some roots go to infinity, and then you can create some auxiliary sequence that is contained and show that it has the same limit. Yeah. Okay. And more recently, we showed that the same is true for the multiplicative convolution of the polynomials. And I also want to tell you a bit about how we showed something like this. Okay, so now I want to give you the proof, but are there any questions before I do that? Okay, so just recall Steinerberger's problem. So you have a sequence of polynomials, the root distributions converge to some limiting measure. And we want to show that as we take TD derivatives, the limiting root distribution of the polynomials is this fractional free convolution of the initial measure. Okay, so this is a three-step proof. The first one is and actually this was done by Mirabelli. It turns out that you can interpret this convolution as a differential operator. So here D will denote differentiation with respect to X. So if you apply it to a function, it returns the derivative of that function. And one can write this convolution in terms of the operator that first takes a derivative of the function and then multiplies it by the monomial X. So to be precise, since we can write this convolution explicitly in terms of coefficients, it is not hard to see that if you have two polynomials P and Q and you want to convolve them, what you can do is find some other polynomial big P such that when you apply it to the operator xt, and then you apply that to x minus 1 to the d, you get P of x, and then find some other polynomial Q such that when you apply it to the operator and then to this polynomial x minus 1 to the d, you get Q of x. Then the convolution can be written as composing these operators and then applying it to x minus 1 to the d. You had a question, Jim? Okay. So, which is, yes, exactly. So you can apply first the Q, or you can commute it and do this, right? And the point of this is that if you fix, say, Q, then you can, and then you take P as an argument, then this is really a differential operator with some monomial being applied to some polynomial. Okay? So that's what Mirabelli noticed. And well, once we know that, since we care about the kth derivative of P, it's natural to say like, okay, well, then I want, this is some differential operator. Well, I want to write it in terms of the convolution. So it's not hard to see that for every k, there's a polynomial such that, a polynomial R such that when you apply it to the operator xd, you get x to the k times d to the k. So you can prove this by induction or directly. And then for this R, it's easy to compute what it does to x minus 1 to the d, right? So you get this polynomial here. Yes. So this interpretation here is only for the multiplicative case. The additive one, yeah, has a different one.
Yeah, it would be similar, but without x, right?
Without the x, right? And without the 1. Yeah. Okay. Yeah. So you apply it to x minus 1 to the d. You get some concrete polynomial, which is what you have on the right-hand side. And then precisely because of what was written in the previous slide, for any polynomial p, if you do the convolution, multiplicative convolution with R, you get this polynomial, x to the k times the kth derivative of p, which is almost what we want. And we'll see that actually it's enough to give us our goal. Okay. So that's the second step. And then the third step is like, okay, well, now that we've managed to write down this kth derivative using the convolution, well, let's use the result that we recently proved, that this convolution converges to the multiplicative free convolution. So recall the setup. You have some sequence of polynomials with root distributions converging to some measure nu. Then what we're going to do is like, we want to take t times d derivatives. So let k be t times d. And then let rd be the polynomial that, well, this polynomial over here. Then by what we showed in step 2, p convolution with this r is going to be x to the kd times the kth derivative of p. Okay. So now it's easy to compute what's the asymptotic root distribution of the r's, right? So the r only has roots at 0 and roots at 1, and it's enough to know what proportion they're in. So it's easy to see that they converge to this Bernoulli here. And then the technical input here is that we know that the root distributions of the convolution will converge to the multiplicative free convolution of the measures, right? So the r's are converging to this one. The p's are converging to nu. So then the root distribution of the multiplication is going to converge to the multiplicative free convolution of those measures. And so now we can use free probability, right? And this, we know this result of Nick and Speicher, that this multiplicative convolution is in fact equal to this measure down here. So this is not exactly what we wanted to get, but that's because we didn't have the polynomial that we really wanted, right? So there's this extra atom at 0, but that's coming from the extra x to the k over there. And once we remove it, we remove the atom at 0 and we recover the, well, the solution to Steinerberger's problem. So just to review, you interpret the convolution as a differential operator. You find a specific polynomial that allows you to implement the differential operator that you care about. And then you exploit that you know how to, well, that you know that the limit of convolutions converges to the multiplicative free convolution of the corresponding measures. And that's essentially the proof. Okay. So, well, I hope that this motivated a bit why to look into finite free probability and also why to study this multiplicative convolution. So now I want to tell you about how we studied the multiplicative convolution and what other results one can obtain with those techniques. So, well, in Andu's talk, there were already the set of partitions and set of non-crossing partitions, which are over there. I believe that the Krevras complement didn't appear. So this is some involution in the set of non-crossing partitions, and this is some definition by example. So you have some partition, you write some numbers that interlace the original ones, and then you connect them using blocks as big as possible without intersecting the previous one. So that's the Krevras complement. And this already appeared also. So if you have some sequence indexed by integers, you can extend that sequence and now index it by partitions where each a pi is going to be defined in this way. So this is just as in the previous lecture. And there was also some mention that you can use cumulants, free cumulants to describe the additive free convolution, for example. So this is the relation between free cumulants and moments. And free cumulants are cooked so that this relation holds. So they're additive with respect to the free additive convolution. But so that's the way they were, well, that's what they were designed for. But maybe something more surprising is something that Nick and Speicher realized in '96, that you can also use these cumulants to study the multiplicative free convolution. So there's this very nice formula that writes the end cumulant of the multiplicative free convolution in terms of the cumulants of each of the measures. And as you can see here, the Krevras complement is appearing. And in general, well, like the high level idea is that you have this pipeline that starts with measures. You can understand measures through their moments. Moments can be encoded in free cumulants, and then free cumulants are cooked so that you can study free convolutions. So in a similar way, in the finite free world, we care about polynomials. Those you encode in terms of coefficients. And then finite free cumulants will organize the information given by the coefficients so that you can study these finite free convolutions. And these were introduced by Arismendi and Perales. And so given some polynomial of degree D, you can write down the finite free cumulants as a function of the coefficients of that polynomial. What that function is maybe not so relevant right now, but it's some sum over the set of partitions. And of course, they satisfy that they linearize the additive convolution. And there's this very nice property that they converge to the free cumulants. So if you fix some n, and then again, you have some sequence of polynomials PD whose root distributions converge to some limiting measure nu, then the end cumulant of the polynomial PD will converge as d goes to infinity to the end cumulant of the limiting measure. Okay, so this poses the question if one can study the multiplicative convolution using these cumulants, and we also saw that the multiplicative convolution is of independent interest in the process. Okay, so what did we show regarding this question? Well, first of all, there is a formula. So on the left side, you have the end cumulant, finite free cumulant of the multiplicative convolution of two polynomials. And the right-hand side is all a function of the cumulants of P and the cumulants of Q, okay? Maybe this is not, or it doesn't look as nice as the other one that I showed you of Nika and Speicher, but actually I want to convince you that it contains that formula and it actually is telling us more. So yeah, for now, don't worry a lot about what exactly these terms are. Here, mu is the Möbius function on the poset Pn. But what you should focus on is these exponents of D, right? So there's some condition on the pairs of partitions that are being used here. And that condition, it's some combinatorial condition that their supremum is equal to 1. It's easy to show that it implies that the sum of their sizes is less or equal to n plus 1, which means that these exponents will always be less or equal to 0. So you can just group all these terms according to what number you get in the exponent, and then you get some expansion in 1 over d, okay? And one of the main messages of this talk is that if you understand well the combinatorial structure of each of these terms, then you can learn something about the asymptotics of polynomials. So for example, if you just ignore all the terms that have some strictly negative coefficient and focus on this leading term, then what we showed is that, in fact, that chi0 can be reorganized in a very nice way, in such a way that you get now the sum over non-crossing partitions, and here you get pi and the Kreyber's complement of pi. So this is exactly the Nyquist-Speicher formula if you ignore the terms of order 1 over d. And what is that good for? Well, that gives you a direct proof that this convolution, finite free convolutions, converge to the free convolution. And so just to make it very explicit, what we're using is this first fact that I told you, that finite free cumulants converge to cumulants. And the second fact we're using is the Nyquist-Speicher formula. So then what you do is like, okay, I want to see what's the value of this as d goes to infinity. So you can push the limit inside the sum because there's only finitely many terms. Now each of these finite free cumulants become free cumulants in the limit. And here on the right side, you apply the Nyquist-Speicher formula, and you just get kappa n of nu p convolved with nu q. So that's telling you that the finite free cumulants of these measures here are converging to the corresponding cumulants. And because cumulants determine moments and moments determine measures, you get this proposition over here. So that's one application. And well, just to conclude, I want to tell you that it turned out that these other terms also have some nice combinatorial interpretation. And actually it's more topological than combinatorial. So in general, what you do, so these terms can be indexed in terms of multi-annular non-crossing permutations on surfaces of different genera. So you take some surface of some genus G, and you take some number of disks on that surface, you remove them, and on the boundaries of the disk, you put numbers, and then you're allowed to connect those numbers as long as you don't get crossings. So for example, this is some torus, you remove 2 disks, and then you connect the numbers in the boundaries of those disks. And non-crossing partitions are a particular case of that, where you start with the sphere, you remove 1 disk, and then you're connecting in the remaining part of the sphere, well, that's going to be another disk, and you want to connect the numbers without getting any crossings. So those are non-crossing partitions, and this first one is just in terms of that because you only see genus 0 at that point, and you only see 1 disk removal. As you go down here, you see higher genera, and you see more disk removals. And this is interesting because these objects appear naturally in the theory of higher order fields, which someone might talk about later. Okay. And okay, maybe it's better to get questions. So if you know what infinitesimal distributions are, we're also able to compute infinitesimal distributions of sequence of polynomials by looking at the formula corresponding to the terms of order 1 over d. So for example, for Hermite and Laguerre polynomials, there's some explicit formula for the infinitesimal distribution of these polynomials that was obtained by Dumitru and Edelman using different techniques. So we can obtain that as a byproduct of our machinery. Okay, that's all. Thanks.